All right, there it is. Okay, let's look at the syllabus here. Let's see, today, the 14th, which is right here. Let's see. So I did set up Monday this quiz right here. Should now be set up. And let's see. Yeah, it looks like there's nothing for next time. So there's no quizzes for me to set up this afternoon. There will be one more quiz in the class over chapter 11, and that's it. I've already told you I'm not going to have you do chapter 12 quiz. We're probably not going to get to chapter 12 in lecture at all. And I'm not too concerned about it. We'll still have plenty of stuff to talk about on test 2, which will be during finals week. I will suggest once again, I've talked to some students about the Master's Emissary paper topics. I've given feedback to several people from that extra credit paper that was turned in several weeks ago. I still encourage people, if they haven't, you're allowed to actually turn in that extra credit paper late. If you have, feel free to send me an email and I can go check on that extra credit paper and give you feedback on it. Even if you have already turned in your extra credit paper, which is basically, it's a paper which is kind of helping, it's like the first step kind of towards deciding a topic. I'm happy to talk about topics and your approach to the paper more. It's definitely helpful in my experience to talk to, it's helpful for the students to talk to them about the topics of their paper, make sure that they're in the right direction, and to talk about kind of the general approach of the paper. I'm not exactly fond of reading the entire paper and just give you general feedback before you turn it in, but I'll definitely have a conversation where you're asking specific questions about your paper and I'm answering them, or I'll read like a specific part, like a one paragraph or so if you have a specific question about that. But I'm definitely okay with having general conversations about your approach and the topic. And I suggest that for everyone. If you haven't done the extra credit, that's kind of what the extra credit is about, is like first step towards that. And I will accept it late if you did the extra credit and you didn't get the full 2 points. I would have given you feedback for that. And you can set up a meeting with me, or if you turn it in again, I will give you the remaining points if you kind of address the thing that I told you to address. Any questions or comments then about things coming up? Assignments, calendar, schedule stuff. Okay. The goal today is to finish chapter 7, which I think is feasible. It's about attention. I do have in-class discussion, quiz, question things that I think we'll probably get to today. Depends on how much time we spend talking, discussing stuff. I did want to briefly review the difference between the type of attention, which is illustrated here in this paradigm, reflexive attention versus voluntary attention. Um, in this reflexive paradigm right here, the attentional cue, at least in this particular version of it, this particular study, was these 4 little circle things that appear very briefly, a 20th of a second, 50 milliseconds, and they're in the reflexive attention, which is also known as exogenous or involuntary, not voluntary attention. The idea is that your attention is kind of stolen. It's kind of taken. Your attention is in one direction, and then something happens. Like the real life example would be like someone in your peripheral vision who's kind of waving their hands, which kind of steals your attention, it pulls your attention in that direction. Or maybe a loud sound would be like an auditory cue that would kind of pull your attention in that direction. And this one, though, it's just kind of like 4 dots, which appear little like white, bright kind of dots that appear in one visual field, which is trying to pull your attention over to this visual field. Can anyone remind me, or you can talk about it, you can add it in the chat part. What is the attentional cue and the voluntary attentional paradigm, also known as endogenous or voluntary attention? What is the attentional cue in that one? And this one, it was those 4 white circle dots things. What is it in the voluntary attention paradigm? Let's take a look here. Yep, a couple people have said the arrow, which is correct, which is a symbolic cue. It's a symbolic cue because it's not like stealing your attention. You see it, you understand kind of the meaning of the cue. You see the area like it means, oh, I'm supposed to uh, attend to the left visual field, or it's pointing to the right. I'm supposed to attend to the right visual field, but you can use kind of your will to determine whether you're actually going to attend to that direction or not. Compared to reflexive or automatic exogenous attention, which is reflexive, as I mentioned last time, it's kind of like when the doctor hits your knee with that little hammer thing and it makes you kick your leg and you don't really have too much control over it. That's where reflexive attention is, kind of takes your attention. You don't really have too much control about it. With the arrow, on the other hand, though, you could think of it as you do have control, voluntary, endogenous. Endogenous, by the way, refers to the fact that it's like an internal thing which determines whether you attend or not. Exogenous, which is what this is an example of right here, means that the thing which determines whether you're attending or not is something which is out there. Exogenous refers to out there in the world, kind of takes your attention. Endogenous, which is voluntary, means that it's something inside me which determines where my attention is going. Yeah, and then so this is where we left off, I believe. And this is the one that we talked about mostly last time. So this is a event-related potential study. And we're looking at they're focusing in here primarily on this P1, though it does look like over here that this is like an N1 that they don't really talk about. It looks like there is a difference there. Anyway, I'm getting ahead of myself. I want us to kind of think about what the short ISI and the long SI means, or what these terms mean here. And to also remember what the difference between the blue and the red traces are on these graphs. So I do mention up here at the top, so this is reflexive cueing, automatic attention, exogenous attention. The attentional cue is these the white boxes, it looks like they're in this study, which highlight either the left visual field or the right visual field. And then there's a target, which in these trials in this experiment appears to be a white vertical rectangle. And when you see that, you're usually doing a very simple task like push the space bar as soon as you can, quickly as possible after you see that target. In this run right here, this would be like the attention trial, or the like a valid trial, because the cue is telling you pay attention. It's pulling your attention over to the left visual field, and then the target occurs in that left visual field. This is an uncued or an invalid trial because the cue is telling you to pay attention to the right visual field, but the target occurs in the left visual field. So there's like a mismatch here. The cue is telling you to pay attention to one side, but the target actually occurs on the other. And so this is the blue trace right here, the cued trials. And then this is the red trials right here, like as far as these traces. So the cue is blue, and then the uncued is the red right there. And I mentioned at the top here, it says the ERP in the study is measured in response to the target. We talked about kind of the 3 different places last time that in attention studies, the event-related potential response can be measured. It can either be measured in response to the cue, which doesn't happen that much, or it can be measured during the delay interval or the preparatory interval, which is pretty common. I did show you a study last time where that was the case, where the brain response was measured during the waiting time. That is after the cue was presented, but before the target was presented. That was kind of the area that the researchers were focused on, the delay or preparatory interval. In this study, though, the brain response is measured in response to the target. And so the target is the vertical white rectangle. And that's what this right here, this represents time point 0. And it also time point 0 right here. This little legend, I think you would call this, also represents right here. This is time point 0. And if you look, there's milliseconds here on the x-axis. The y-axis is voltage. There's the negative side. And then there's the positive side. Positive is down, negative is up, which might seem a little counterintuitive, but I have mentioned that's kind of common actually in ERP research. It's been the convention for many years. Some people are starting to change it now, and they'll put positive up and negative down. But the convention for the longest time has been, in general, positive down, negative up on the y-axis. So last time we did talk about the short versus, we talked a little bit about the short ISI and the findings. So the short ISI means interstimulus interval, um, which is a fancy word. Really, it means the amount of time between the appearance of the cue and the appearance of the target. So like the amount of time between these two like parts of the trial right here. Similarly, the amount of time between these two parts of each trial right here. The amount of time between the cue and the target, the amount of time between the cue and the target. That is an ISI. On some so one of the factors clearly in this experiment was the length of time of the interstimulus interval. There was a short duration interstimulus interval, meaning the amount of time between these two things is only 50 milliseconds, very short. And then there was a longer, there's a condition where the ISI was longer. So the amount of time between these two things was like 250 milliseconds, if I'm recalling correctly. So short and long amounts of time. Neither of them is actually long in the big scheme of things, 50 versus 250 milliseconds. In both of those situations, the ISI duration was less than a second. But here is the brain's response in the reflexive cueing paradigm to the attended and unattended trials, or that is the cued and the uncued trials, for the short ISI. And the brain response is not particularly surprising, I don't think, at least, that your brain's response to the target, you can think of this here for the short ISI, is kind of enhanced when the cue directs your attention over to the side of space that the target occurs only 50 milliseconds later. And you can see that because if you look at the P1, and why don't we just kind of refresh ourselves here? There's these two components. P1, this is a component, an ERP, a common ERP component. What do those two things in the P1 stand for? What does the P and what does the 1? Go ahead and write that in the chat feature, Zoom. What is the P and what does the 1 stand for in a P1 event-related potential? I did mention this last time. Something students sometimes forget. So go ahead, see if you can write that in there in the chat feature. What does the P and what does the 1 stand for in that event-related potential? Let's take a look. So I got a lot of people know that the P stands for positive. Not as many people seem to be understanding what the 1 stands for. I'm getting some. Yeah, I've gotten some. The 1 stands for the first peak. Yeah, a lot of people are saying like the 1 stands for the peak of the graph, which is kind of accurate, but you want to be a little bit more specific. That 1 stands for the fact that it's the first peak. It's the first positive peak, to be specific. The first positive peak, or the first positivity. So there's really not this kind of near zero here, but then around 100, 150 milliseconds, the electrical activity from the brain kind of heads to the positive direction. And then it turns around here. So there's like a point of inflection around 150 milliseconds. That's the peak. P1 is the first positive peak. And a point of inflection, by the way, is just like where the signal is going one direction, then it turns around. That's a point of inflection. And so the P1 measurement of the ERP, the response is bigger for the cued condition than the uncued condition, that's not hugely surprising. When a target appears at the point of space that you're attending to, your brain responds to it more strongly, which that makes some sense to me, some intuitive sense. When you're ready for something, it's your attention's over here, and then the thing that you're supposed to respond to comes over there as well, just 50 milliseconds later. It's like your brain is ready for it, and so it responds more strongly to that thing when it occurs over there. So the blue has a stronger voltage, is more strongly in the positive direction than the red. Makes some sense. That's for the short ISI, when the amount of time between the cue and the target is only 50 milliseconds. There's a pretty counterintuitive finding that occurs for the P1, though, for the long ISI. So the long ISI, once again, the amount of time between these two things, the cue and the target, is like 250 milliseconds. So it's 5 times as long. It's still pretty short in the grand scheme of things, but it's 5 times as long, 250 instead of 50 millisecond duration between cue and the target. And you kind of get like the opposite thing, which is pretty surprising. And so let's focus here again on the P1. And if you look here for the long ISI, you actually see that the red, which is the unattended condition, the uncued condition, has a longer, or it has a bigger positivity compared to the blue. The blue actually has less of a positivity here. So this is surprising because basically what this is saying here is that the brain responds in the long ISI more strongly to the target when the target occurs in the unattended side of space. That's surprising. The brain's response for the long ISI is stronger when it occurs in the side of space that you're not expecting the target to occur. It's just surprising. They're like two basically almost, I don't want to say contradictory, but they're kind of like the opposite results. When there's a short ISI, your brain responds more strongly to the stimulus that's in the attended visual field. In the long ISI, when the difference in time is between these two things is 250 milliseconds, you kind of get the opposite thing. The brain response to the unattended target is more strong than the brain response to the attended target, which is just kind of surprising. And there is a term for this that they talk about in the textbook. And I do want you to be familiar with this term. So I'll go to it. I think it's the next thing. Yeah, inhibition of return. I don't believe I was thrilled with the way it was explained in the textbook. So I think I've kind of changed things up a little bit here to try and make it more clear. But that's exactly what is illustrated by that. The difference in the ERP response between the short ISI and the long ISI for that study I just showed you, that reflects inhibition of return. For those longer durations, the longer ISI, that P1 ERP, the first positive peak brain response to the target, which is that right rectangle, was smaller than in the uncued location. That's the inhibition of return idea, is that you actually kind of, your attention is kind of inhibited when the amount of time between that reflexive cue, which kind of steals your attention, if there's too long in between that reflexive cue occurring and then that target occurring 250 milliseconds later, kind of a relatively longer amount of time between those two things compared to 50 milliseconds. If that amount of time is too long, then you kind of lose the attentional advantage that you would compared to when the ISI is small, 50 milliseconds. That's the inhibition of return. And there is an analogous effect in reaction times as well. So I want to kind of go back real quick, just talk about the same study in terms of a reaction time, even though I don't have the graphs for that. For this graph right here, like if we did the exact same thing, but instead of measuring brain responses, instead of measuring the electrical activity, we just had people respond to this thing, this target, as quickly as possible. And then the researchers were measuring the dependent variable reaction time. What you would expect based on the brain responses here is that for the short ISI, we would expect reaction times to be quicker for the attended condition compared to the unattended condition. The idea here is that when the brain response is stronger, you might think, okay, that means the brain is more prepared for the target stimulus. If the brain is more prepared for the target stimulus, you would expect the participants to respond to it more quickly. So for the short ISI, the prediction based on these brain data would be quicker responses for the cued, the blue condition, compared to the uncued. You would expect quicker reaction times when the target occurs in the attended visual field compared to when the target occurs at the unattended visual field here. Quick responses you'd expect here, and you would expect relatively slower responses here for the short ISI. The idea of inhibition of return is illustrated once again for the long ISI. If you were using reaction times, you would expect the exact opposite thing to happen that you saw compared to what you saw for the short ISI. For the long ISI, for reaction times, you would expect that reaction times would actually be quicker for the unattended target compared to the attended target. When the ISI is long, when the amount of time between these two things, the cue and the target, is 250 milliseconds, kind of a long, relatively longer ISI, you would actually expect a counterintuitive finding based on what you're seeing here in the brain. The brain's response to the unattended object, unattended target, is actually bigger than it is compared to the attended, the cued object. And so if you interpret a bigger brain response, meaning the person is more prepared for whatever reason, then that would translate into behavior that the person should respond more quickly to that thing. The red trace has more of a brain response for the positivity here. That red trace represents the uncued, the unattended condition. When there's the cue appears on one side of space, but the target occurs on the other, the brain response is bigger. So although it's kind of surprising, you'd expect quicker reaction times for that condition, the uncued condition, compared to the cued condition here. And that illustrates inhibition of return, kind of this counterintuitive finding, the difference in brain and reaction time, that is behavioral responses that occur in attentional studies, particularly the reflexive attentional studies, the difference in brain and reaction time responses between that short and long ISI. And I'm not really for sure the reason why this effect occurs. The textbook, if you're curious, does provide an explanation. I don't find it particularly compelling. I'm not for sure if that is the correct explanation or not. So I'm not going to focus in too much on it. It is a phenomenon that exists. And I would have to say that the explanation for the phenomenon of inhibition of return, the differences in the brain and behavioral responses between those short and long ISIs, I don't think the cause of that kind of almost contradictory results, I don't think the cause is agreed upon by many cognitive neuroscientists. Okay, so yeah, this is some fun stuff, kind of most of the remainder of the chapter is pretty fun stuff, at least I think the more interesting aspects. And it's also relevant because a lot of this stuff is connected to ideas in Master and his Emissary. So these are some of the parts of this chapter which are most closely related to some of the stuff which is focused in on Master and his Emissary. So the textbook kind of talks about, these are conditions when attention fails or when there's attentional problems. And the one that we're going to talk the most about is neglect, which is more common than this other one. I believe this is pronounced balance syndrome. Balance syndrome is more severe, but it's also way less common than visual neglect, hemi-neglect, as this is oftentimes called. So balance syndrome has these different components, and overall, there's just more problems, more issues that an individual with this condition has compared to a person with neglect. And neglect is a serious condition. Balance syndrome arguably is worse because it has kind of these two motor components, which is what these are. Ocular motor problems, meaning the control of the movement of your eyes. You know, most people can control their eyes, no problem, from left to right, and you can, follow a moving object, no problem. If you have balance syndrome, your ability to kind of control your eyeballs and to follow something which is moving around in your environment, that's going to be something which is difficult for an individual with that condition. Optic ataxia, similarly, is a motor problem, but it's not a motor problem with the eyes as much as it is like a motor problem with your hands. Difficulty engaging motorically with objects as they appear out in as they occur out in space. I guess you could kind of think of these as you have trouble kind of paying attention to where something is in space, or processing kind of the spatial arrangement of things out in the world. And so you have problems representing them spatially. And I guess the idea, and you can think of it kind of in terms of like that dorsal pathway, that parietal or the where pathway, is if you can't represent things spatially, if your brain isn't able to represent where objects are out in space, then your body, including your eye movements and your hands, is going to have problems interacting or following with those things spatially as well. You have to be able to represent the things out in space if your body is going to be able to interact with those things. So both the eyes and the hands, you can mostly think of it, have problems interacting with objects where they occur in space. Those are two motor components, two different kind of motor systems, the eyes and the hands. Visual simultagnosia, I'm not going to talk too much about this. If I recall, the book doesn't actually present too many examples. I will say, though, that it's different than these two right here. These two are mostly motor impairments. Simultagnosia is a perceptual impairment. It's the idea that you have problems perceiving and representing the visual appearance of scenes, visual scenes in particular. The idea here is that visual scenes kind of have multiple components. I think the terminology is people with simultagnosia have a problem kind of representing the different components of a visual scene simultaneously. There's a lot of stuff going on in a visual scene, and most of us can kind of represent all of those different things in a scene kind of simultaneously. But an individual with visual simultagnosia, they can only represent like a single element of the scene at a given time. And so they have kind of problems perceiving the entirety, the holistic or global aspects of a scene. I think we have a question or comment here. Let's take a look. So the question is, so does this cause impaired vision or just inability to find objects in space? I would say the second thing you said is probably a more accurate description. It's more of a problem with locating things in space. I would say it's not like an impaired vision per se. At least when I think of impaired vision, I think of like nearsightedness or farsightedness or astigmatism. I think those are like problems related to like the eye. You know, like in particular, I think nearsightedness and farsightedness, these are visual problems, impaired vision, because they're like problems with the lens, like the way that light is focused in on the retina, that back part of your eye. That's what I think of visual impairments that are problems specifically with the way the eye directs light towards your retinas. Those are what I consider to be the visual problems. The problems with balance syndrome are connected to the brain. So they're visual problems, mostly motoric, but some perceptual. Simultagnosia would be considered perceptual, that are related to brain issues, things in our brain. And so, yeah, I would say perceptually, one way you can kind of think of it is having a difficulty here localizing objects in space, but also representing the different elements of a scene. If you imagine trying to think of like a painting that has a whole bunch of stuff, or just, you know, like a city scene where there's a whole bunch of different things going on simultaneously, a crowded scene, a person with simultagnosia is going to have a hard time kind of processing the various elements of that scene. They can focus in on each element and they'll probably be able to see the individual element by itself, but they have a hard time kind of seeing the elements in the overall context, kind of the global context. Let's see if this is another question. Is this syndrome a cause of cortical vision impairment? I'm not actually for sure what you mean by cortical vision impairment. I'm not for sure. That must be a term in the textbook, perhaps, that I'm not familiar with, or it's a term that you've heard somewhere else. Cortical vision impairment. I've not heard of that term before. I mean, it seems accurate. It's definitely a visual impairment, and it's caused usually by problems with the cortex. Although some of the problems related to these motor issues could also be caused by subcortical issues, so like below the cortex. I would definitely say all balance syndrome is definitely caused by various visual impairments, and motor impairments are caused by issues with the brain, though they might not all be cortical per se. I would not say the brain basis of this is incredibly well known, but I would say there's probably not just cortical. So remember, the distinction, cortical is like the top parts of the brain, the more evolutionarily recently evolved parts of the brain. I would imagine that these motor issues in particular, there could be some subcortical abnormalities which are contributing to those. But in either case, balance syndrome, it's a brain. These visual issues are related to the brain. So neglect is the one that I want to focus in on because it's most relevant to the master and his emissary. Let's see, make sure that I didn't. Okay, so the student is explaining what cortical vision impairment is. My mom teaches blind kids. Cortical vision impairment is when your eyes work fine, but the brain isn't able to interpret what you're seeing. Yes, I would say that this is balance syndrome and neglect are both cases where your eyes themselves appear to do what they're supposed to. And really what the eyes are supposed to do is take in light and then direct that light in a focused way onto your retina, so that the different receptor cells, rods and cones on your retina, can send those signals to the brain, and the brain can then interpret those signals. These problems here, the eyes themselves appear to be directing light effectively. They're able to take that light and direct it towards the retina. But then something is happening after that, generally, with these conditions, which causes the information which is sent to the brain to have you're welcome, have problems being correctly interpreted. So yeah, I would say that this is one example. It's not the only example. There are other types of brain-related cortical vision impairments, using your terminology, that could occur. This is just one of them. There are like two of them. These are two different, I guess you would say, CVIs if you're using your terminology, cortical vision impairments. Though we'll say once again, they're not necessarily cortical only. There could be some subcortical components, especially of the motor things here. Moving on to the neglect, though. So good questions, by the way. Moving on to neglect. So this is something talked about in Master and His Emissary in kind of different forms. There's the visual neglect, is what they definitely talk about in Master and His Emissary. Visual neglect, it's usually occurs, I want to see what I have in the next slide. Yeah. Usually occurs after right hemisphere damage. In this scene, so this is another, there's more evidence of a hemispheric asymmetry, which is why Master and His Emissary likes to talk about neglect a lot. The hemispheric asymmetry is that if you're going to have visual neglect, it's most likely to occur when you have damage to the right side of your brain. If you have damage to the left side of your brain, that's less likely to cause visual neglect. And what neglect is that it's, I'm not going to say it's a seeing problem, but it's difficulty attending to objects or information, things in one side of the world. So if you have a lesion to the right hemisphere and it causes neglect, which is the most common situation, you're going to have problems paying attention to things in your left visual field. Although, and conversely, although it's much less frequent, you can have a left hemisphere lesion, which will cause you to have problems attending to things in your right visual field. So basically the contralateral visual field, the contralateral hemifield, relative to the location of a lesion in your brain. In that contralateral visual field, you're going to have problems attending to things if you have visual neglect. And as I mentioned, it's most common with right hemisphere lesions. So the most typical way that this occurs, you have damage to your right hemisphere, which is going to cause problems attending to things in the left visual field. So if you have neglect in your right hemisphere, will you also have problem with motor movements in your left visual field? I think so. Yeah, I would probably. I mean, it depends on some things. So I'm gonna present here on the subsequent slides kind of a person with visual neglect doesn't always show the symptoms of neglect. It's neglect, and I'll kind of jump to the punchline, but then I'll have to explain why this is the punchline. People with visual neglect, like a right hemisphere damage, would cause problems paying attention to the left visual field. Those impairments are much more likely to occur when there's a lot of stuff going on in the visual scene. If it's a very sparse environment, if there's not a lot going on, a person who has neglect of the left visual field can often, sometimes, still pay attention to things in the left visual field. But if it's a very complex, crowded scene, then those impairments, the difficulty attending to the left visual field increases. In those situations where you really have trouble attending to things in the left visual field, you would imagine there are going to be motor impairments. Your ability to interact with those things that might occur in the left visual field. If you can't attend to those things, then how are you going to reach for something? Which is, you can't reach for something, or it's going to be difficult to reach for something if you can't attend to it in the first place. So I would imagine you would have motor movement issues. And I also want to, so yeah, another good question. I also, it kind of reminded me a loose connection of another, before I start kind of talking more details about neglect and how it's studied by neuropsychologists, I also wanted to mention a form of neglect, which is like body neglect, which is talked about in the Master's Emissary. If you watched all my lectures, I've talked about it some in those, the Master's Emissary lectures, but the asomatognosia, very long, asomatognosia, 7 syllables, I think, if I just did that correctly, 7-syllable conditions, the typical way, asomatognosia, very long word, which is kind of a type of body neglect. There's a clear connection, though, between just regular visual neglect and asomatognosia. And visual neglect, the thing that you have trouble paying attention to is visual things out in the world, in the left visual field. With asomatognosia, this is kind of that strange condition where people will kind of have trouble paying attention to the left side of their body. So it's a type of neglect, but it's like body neglect. And the interesting connection is that asomatognosia also is way more likely to occur with right hemisphere damage than left. In fact, I don't know of any examples. I've looked through some studies, and every example of asymptomatognosia I've seen also occurs with damage to the right hemisphere. I've never seen one where it occurs after unilateral damage to the left hemisphere. But asymptomatognosia is that kind of condition where some people, there's like anecdotes about this from various patients who have asymptomatognosia. They will not recognize that the left side of their body belongs to them. And so there's these weird situations where a researcher or a doctor will ask, so whose hand is this right here? They'll literally point to the patient's left hand. And then the patient will deny that that belongs to them. They'll say, no, it's not mine. They'll say something, sometimes like a classic examples will be like, oh, it belongs to my mother. And they'll like attribute this hand, which is to everyone else, very clearly connected to their own body. They'll attribute it to someone who's not even in the room with them. And they'll be like, I don't know how that got there. What's that doing? What's my mom's hand doing in my bed? It's kind of shocking because everyone else is like, oh, that hand is definitely yours. But they oftentimes will not acknowledge that the left side of their body belongs to them, and they'll say it belongs to someone else. It doesn't happen with the right side of the body, though. If you say, whose hand is this? And you're pointing to the right hand, they'll be like, oh, that's my hand. But if you point to the left hand, they're much more likely to deny that it belongs to them. So it's a type of neglect of the body, asymptomatognosia. And an interesting connection is that for both visual neglect and asymptomatognosia, problems attending to the left side of things, either the visual world or your own body, both are more likely to occur with lesions of the right hemisphere. So it's an interesting little connection between visual neglect and asymptomatognosia. But I wanted to talk more about how like unilateral spatial neglect or visual neglect, spatial neglect, hemi-neglect, these are all the different words that are oftentimes used, or just visual neglect, how they're kind of identified by usually doctors, but researchers as well, who are studying the patients. And so I think some of these pictures are actually, some of these should look familiar. I'm pretty sure. This is one of the reasons I told you. It's very clear to me that Ian McGilchrist, the author of Master and His Emissary, read the textbook that we use for the class. Obviously, it was an older edition because the Master and His Emissary was written several years ago, before the 5th edition of our book was even existed. But he clearly read a previous edition of our cognitive neuroscience textbook by Gazzaniga, because many, at least appears that way to me, because many of the same pictures which are presented in our textbook also appear in Master and His Emissary, including some of these. I don't remember this one. Probably this clock is one, maybe the picture of this. I don't remember exactly which, but all of them illustrate visual neglect. So a classic example would be an individual with visual neglect who can't attend to things as easily in the left visual field because of right hemisphere damage. When they're asked to draw a clock, they'll make a clock that looks like this, and you kind of notice that the left side of the clock is missing most of the numbers. They did get that 7 there, but obviously there's a whole bunch of numbers like 8 through 11 are missing. Another weird thing, which I don't really know what to make of it, is that they also sometimes repeat numbers. Like it says 12, 1, 2, 2, 3, 4, 5. And then like they write the number 6 as well twice. I'm not really for sure how to explain that. The most striking, though, feature here is the left side of the clock is missing. Here's a visual scene. They're asked to draw this. So it's not super hard for most people to draw this scene. But when individuals with visual neglect are asked to draw that scene, the left side of the scene is clearly missing. And if you look closely, another interesting element, in my opinion, is that they also, now the left side of the scene, like the global aspects of the scene, are missing. But if you look at the specific objects themselves, like the house, the left side of the house is missing. If you look at the trees right here, these are on the right side of the scene. But if you kind of zoom in on a tree as though the tree is its own scene, they kind of make the right side of the trees like bigger and more pronounced than the left side. Like the left side is kind of small. It's like not going out as far as it should. The right side is, full of this tree, and the left side is kind of thin. And similarly over here, which is different. Like these trees, if anything, the left side is slightly bigger than the right. And I hope you understand what I mean. By the left side, I mean like the difference from the far edge to the center is kind of a longer distance here than it is here. So the left side is actually pretty big or fat here for this tree, similarly over to here. But when they actually look at the trees that the individuals made, they kind of neglect, even though they saw that the trees exist here because the trees are on the right side of the scene, when they're kind of drawing each tree individually, there's a tendency for them to kind of have problems representing or paying attention to the left side of the tree itself, which makes them in all cases, they focus in on the right side of things, whether it's the entire scene or whether it's the individual objects within the scene. They focus more on the right side of the objects and ignore the left side of things. And then another example here, this cat at the bottom, they're asked to draw this, which kind of looks like a hard thing to draw actually, but they draw something which is more like this. And the idea is that they are missing the left side of the cat once again. So visual neglect, much more likely to influence the left visual field. So here is yet another example. This one I like. It's a common, it's just a straightforward kind of neurophysiological way of kind of identifying individuals that might have neglect. So the line bisection task, and your task as a participant, you see all these horizontal lines, and your job is to bisect all of them. And so bisect means to put a vertical line through each one so that it cuts it in half. It looks like we have a question or comment here. Let's take a look. Your question is, can the person tilt the image, like draw it top down and still have this issue? I'm not for sure. I don't know if I understand your question. Maybe rephrase it and see it and ask it here again in a second. Let me explain kind of the line bisection task, and then maybe see if you can be a little more specific with your question, and I'll try and answer it. So the line bisection task, your job is to put a vertical line through each of the horizontal lines here. And you want, by bisect, I mean, you want to put it right in the middle. That's what bisect means. Vertical line, which evenly divides the left and the right side of the line. So you get something like this. And for instance, if I was performing the bind, if my mouse was my pen, I would put like a mark right there. I would put a mark right there. I would put a mark right there, there. I'm doing it fast now, there. And then all of these, I'd put a mark right through the center. That's what you're supposed to do. A person with visual neglect, though, like this, would perform like this. And there's kind of two elements, or at least two kind of things that they're doing here, which illustrate that they have neglect. First, they actually appear to not notice some of the horizontal lines on the far left of the scene. If you consider this all a scene, an individual with neglect, they're not paying attention to the left side of the scene, so they miss some of the horizontal lines on the left side of the scene. But even for the lines that they do correctly put lines that they do see, and they put a vertical line through, like this one right here, remember they're asked to bisect. And to me, if you're bisecting this, you would put the line somewhere like closer to like right here. That's more like where the center of this horizontal line is. But if you look, the patient, they bisected it, or they put their vertical line way to the right. It's like too far to the right. The idea here is that when they're kind of focusing in on each individual horizontal line, so they like, oh, there's a horizontal line, I need to put a vertical line through this. Where is the center of this line? And then they're like, oh, the center is right there. And you're like, well, why would a person think this is the center? If you have visual neglect, it's most likely to cause problems where you can't pay attention to things in the left visual field. And so in essence, they're not able to kind of represent this or pay attention to this side of the horizontal line. So it's almost as if the only thing that they're able to pay attention to is kind of the part that I'm circling right here. They're missing the left side, the part which I'm not circling. And so when they bisect it, they base it on only the information that they're able to attend to. And based on that kind of subset, the attentional space that they are able to represent, this would be considered a bisection. They're kind of through the center of what I'm circling here, but they're not able to represent the left side of the line. And so they make their line too far to the right. I'll see if we can get this question again. Like draw a tree sideways, would you still draw half the tree or omit the trunk? Yeah, so if you draw the tree sideways, I think that they would be more like, so if assuming that the trunk is on the left side. So if you, here's a crayon. So this is our tree. A person with visual neglect, when it's standing straight up, would kind of ignore the left side of the tree a little bit. If these are the leaves and stuff, they would omit some of the stuff on the left side of the tree. But if you made the tree sideways like this, yeah, the prediction would be that then if this is now the trunk, that they would kind of miss the trunk. They wouldn't be drawing that, and they would get the leaves correct probably, because those are now more in the right visual field. But if the tree was sideways, if it was oriented sideways, the stuff over here, which would be like the trunk, that is the stuff that they would probably miss. Okay, so I understand the question now. Let me know if that didn't answer it. Okay, so some more evidence. This is evidence using eye tracking. Eye tracking is a cool method where basically a computer is able to track exactly where your eyeballs are looking. So usually you kind of put your chin on this little thing, which keeps your head still. And then a computer, like, some type of a sensor, is able to kind of find your eyeballs, and it can kind of track the movements of your eyeballs like constantly, every movement of the eyes. The sensor, which is connected to a computer, can measure. So it knows basically where your eyes are looking at all times. And so they do this type of research with individuals with neglect, and that's what's shown here. You're like a visual search task where you're trying to find a target which is somewhere in a scene. And these little blue lines, these represent where the eyeballs look. And you can see for a regular control participant, that is a person who does not have neglect, they kind of scan the full visual scene. They scan the left side of the visual scene, and they scan the right side of the visual scene. Though a person with neglect, at least in this case, which is pretty typical, they basically don't look at the left side of the screen at all. Their eyes tend to focus only on that right side of the screen, and they tend to their eye movements almost are like there is nothing on the left side of the screen. They're not able to attend to things over here. Someone asked a question earlier, if you have visual neglect, might it cause problems like interacting with things motorically? This is pretty clear evidence that the answer is yes. If you have visual neglect, your eyeballs, when they're scanning the scene, will tend to scan in the direction of the right visual field, the right side of space only, and kind of ignore the left side of space. And that's because you can see all the blue lines are over here on the right side of space. And there's really only that one little blue line right here, which kind of goes into the left side of space, but it's very brief. And then the great majority of the time, they're scanning the environment over here. So more evidence of neglect. This is motoric. The eye movements themselves tend to focus on the right visual field. I really like this idea right here, extinction. This is a neat one, and it's connected. I'd say one of the more bigger picture themes of this chapter is this idea of extinction. And then they also talk about this, the biased competition model, which I'll be talking about in a second. They're kind of two related ideas. This idea of extinction is probably the most like straightforward way of understanding this idea, but it's quite related to this biased competition model. The biased competition model is kind of like how the brain works during attention. Extinction is kind of more of like this behavioral elements of this. So biased competition model is a little bit more, which we'll get to, a little bit more complex in the sense that it's talking kind of more specifically about what the brain does, but they're definitely related. So yeah, this extinction idea, I think it talks about it explains those situations where the visual neglect is most likely to occur. So as I mentioned earlier, visual neglect does not always occur. An individual that has visual neglect, sometimes they will actually be able to attend to something in the left visual field. A lot of times they won't, but sometimes they will be able to attend to something in the left visual field. I already told you kind of the punchline. Now I'll kind of explain how the research that supports this punchline. The punchline kind of is, in those situations where the scene itself or the environment is sparse, meaning there's not a lot of stuff going on, the scene is simple, it's not complex, there's not a lot of things, and those things are kind of easy to process, doesn't require a lot of effort to kind of understand and process. Those are the situations where you're least likely to have a problem paying attention to the left visual field. But as the scene becomes more cluttered, more chaotic, more complex, that is when you're more likely to have these problems attending to the left visual field. So these three little examples here, they I think very nicely explain this idea of extinction and how in visual neglect. So here's an individual who has presumably right hemisphere damage, which causes left visual field neglect. And the task that the researcher performs here is they're holding up two hands. So this one right here would be in that person in the green shirt. This would be in his right visual field. So he should be able to process this one, no problem. The other hand, which is like this is in his left visual field. So this is the visual field, which sometimes that guy in the green shirt should have problems processing things over here because this is the left visual field. So the task that the participant performs, the researcher says, okay, point to the finger which is wiggling, something along those lines, something like that. Point to and so the wiggling finger right now is in the individual's left visual field, but the environment is sparse because there's not a lot going on. There's one thing which is moving, and that one thing which is moving is in his left visual field. But because the environment is sparse, it's simple, it's not complex, just one thing is moving. The individual has no problem being able to, oh yeah, I see it, it's right there. So in this situation, he is able to recognize, he's able to attend to something in the left visual field. Similarly, and this one is definitely not surprising, if you do the opposite, so now it's like this and point to the wiggling hand, he can see it, no problem here, but this one's not even close to surprising because this one is in his right visual field. And people with neglect are almost always able to see something in the right visual field. So this one's not surprising at all. The neglect becomes really apparent, and it illustrates extinction in box C right here. So in box C, now the environment's become more complex. And it's become more complex because now there's two things which are moving. So it's not super, super complex, but it's definitely more complex than it was in A or B. In A or B, only one thing was moving. Now in this scene, two things are moving. The scene's gotten more complex. It's become less sparse, more complex. And then you ask the individual, point to the fingers which are moving. And as you can see in box C, the individual points to the fingers which are moving in the right visual field, but fails to notice that there are wiggling fingers in the left visual field. So the idea is that your ability to attend to something in the left visual field becomes extinct, or you lose it when there's competition. And competition basically means complexity. There's a lot of things going on, and some of those things that are going on are occurring in your right visual field. The right visual field is that field that you're fine processing things over there. There's never a problem over there. If there's something occurring over in that right visual field, and there's also something occurring in the left visual field, complicated thing, it's a lot going on. The right visual field kind of steals your attention, and you're not able to bring it back to the left visual field. Your ability to attend to the left visual field becomes extinct. That's kind of the idea of extinction. Oh, I wonder if we have a question that I missed here. I'll take a look. Oh, there's just, thank you. You're welcome. Delayed. You're welcome there. So that is extinction right here. The thing that becomes extinct is your ability to attend to the left visual field, which is illustrated right here. It happens when the scene becomes more chaotic. Whatever thing is occurring in the right visual field, which is your strong visual field, the field you're good at seeing, that steals your attention, and it like takes it and it won't share it with the other visual field. It won't allow you to bring it back to the left. And that's what happens. That's like the idea, like it's pulling your attention over here, and you can't switch it back so that you're paying attention to the left visual field. So competition causes extinction. Competition from things in your strong visual field causes a competition, which eliminates, extinguishes, makes it difficult to pay attention to things in your weaker visual field. Would that happen in the dominant contralateral visual field? Not suffering from neglect was blocked like an eye patch. Hold on. I don't know. I don't know what an eye patch how that would affect. That's an interesting little study. I don't think it's been done. So I don't know the answer. And I'm not really for sure of what to expect if you do this with a person wearing an eye patch. And I don't know which eye you would want the person to be wearing an eye patch over. But I'm not really for sure. I would have a hard time making predictions there. The other question is there a certain amount into a visual field where the attention cuts out? Yeah, I'm sure there is. I don't know how that's been quantified or measured. I think what you're saying is, you're at the question that the student's asking is, at what point does this extinction occur? Like, how much competition do you need to have to cause extinction to occur? You know, you can normally pay attention to the left visual field when it's this sparse, simple environment. How complex do things need to be before you're no longer able to do that? And I don't know how that's been quantified. The thing that I do know, and the thing that's been experimentally demonstrated, is that the more things which are in your strong visual field, the less likely you're going to be able to attend to things in your weak, that is your left visual field. So I just think of it kind of like of a linear relationship. The more complexity, which is over in your right visual field, the more things going on over here, the harder it is to pay attention to things going on over here. If there's nothing going on in the right visual field, there's no competition, then you'll be able to pay attention to the left visual field just fine. But the more competition that occurs in the right visual field, the less likely you are to pay attention to something in the left visual field. So I just think of it as like a linear relationship. The more competition that you have in your good visual field, the less likely you will be able to attend to something in your less good visual field. Let's see how we do on time. Not bad. I do want to get through these studies though, for sure. Maybe not all of them, but definitely these first couple. So now I'm going to talk about the biased competition model, which I mentioned just related to this idea of extinction. I think they're very closely related. And except for the fact the biased competition model, this is more related to like, what exactly is the brain doing? So it's kind of like explaining how the brain is used to pay attention. And kind of the punchline, once again, of the biased competition model, similarly to extinction, is that in those situations where there's competition, that's when attention is most important. When there's a lot of noise or chaos or complexity in the environment, that's when you having good attentional skills will be most important. And so the prediction of the biased competition model, which is shown in the study I'm about to talk about, is that in the situation where there's competition, when the environment is more complex, the environment is kind of more chaotic, those are the situations in the brain where you should see more attentional modulation. That is, attention should boost performance more in those situations where there's chaos and you have to focus in on one thing in that chaos. That's when you should see the increase in the brain's response. When things are very simple and you ask a person to pay attention to something which is very simple, the attention isn't going to do that much because it's already very easy to kind of pay attention or to process something which is very simple. But when things are complex and then you look at what the brain's doing, the brain's response is much different to a given object when there's a whole lot of stuff around it. There's competition, there's chaos around it. You need that attention in the brain should increase the brain's response when it really has to work hard. That's kind of the idea for the biased competition model. And that is shown here, a sequential condition, a simultaneous condition of this experiment. So there's kind of this task, you are shown, there's in this sequential condition, you are shown each of these 4 different types of pictures, each one for 250 milliseconds. And one of these is like a target. And when you see the target, you're supposed to respond, being like, okay, there's the target. You press a button when you see the target. One of these 4 is the researcher tells you, okay, when this is the target, when you see this one, I want you to respond as quickly as possible or something like that. And in the sequential condition, each picture is presented by itself. So please notice that there's no competition here, which I don't know which one of these would be considered the target in a given experiment, because it'd change. But in a given trial, one of these would be the target, and you would respond when you saw the target among these. But notice that each one is presented by itself. There's no competition from other visual things here. There's no competition here either, because the thing is presented by itself. There's no competition here either, and there's no competition here either. One of these is the target, and it's going to be easy to find that target when it appears, because when it appears, it'll be by itself. There will not be competition from other things on the screen, so you'll be able to, your brain will, No problem finding it. You won't there. It will not be a hard task for most people because there's no competition. Each of the squares appears, each of the little colorful square things appears by itself on the screen. No competition. The environment is simple. It is sparse. It is not complicated. That's the sequential condition. The sequential condition is things are simple. The simultaneous condition, though, it's kind of like a similar task. You're once again asked to like focus your attention on one of the colorful box things. One of these four things is considered a target, and you'll maybe respond to it when you see the colorful box thing. But here in the simultaneous condition, all four of the little colorful box things, they appear at the same time, simultaneously. You have to focus in on the one, which is the target. And to do that, you have to kind of sift through all of these things which occur simultaneously. This is a much more cluttered, a much more complicated environment. It's more chaotic, I guess you could say. There's definitely more going on. And so this would be the condition that you would expect attention will be most important. You have to find a target here, and you have to have good attentional skills to do that, because you kind of have to ignore the things which are not targets so that you can focus in on the thing which is the target. You don't have to do that in the sequential condition because each colorful box thing occurs by itself. These are simple, not complicated environments. They're sparse. Here, though, in the simultaneous condition, all four colorful box things occurs simultaneously. So you should need attention to focus in on that one, which is the target here. And here is kind of I'll show you another graph here that kind of illustrates what happens in the brain. But I'll tell you the punchline first, and then I'll kind of flesh it out by looking at the figures. And that'll be the last study that we do today. The attentional effects are biggest when there is competition. So as I said, the hypothesis would be the attentional modulation in the brain should be bigger in this condition, the simultaneous condition, than it would be in the sequential condition, because there's competition in the simultaneous condition. There's more noise, more clutter when your target is presented. That's the moment the target is presented, there's clutter, it's complex, there's more competition. And this modulation occurs particularly in V4. So V4 is a relative, like compared to V1, which is the other brain region that they're studying. So these are two visual regions, both kind of in the occipital lobe. V1 is kind of like the earliest visual region there is. It's the very first visual region in the occipital lobe, which is activated. It's early. It's more on the sensory. It's more on the bottom up side of things. V4, it's also in the occipital lobe, but it's relatively later. It's more on the perceptual side, more on the interpretation side, later, more top-down perceptual side of things. And the finding, which has actually been shown in kind of a lot of studies, it's an interesting little feature of the visual system, and maybe a feature of the brain in general, is that attentional modulation tends to be bigger in kind of those later visual regions. V4 is relatively later than V1. And what they find in V1, there's not very much attentional modulation for either condition. There's not, no matter which condition you are, the brain's response to V1 and to the sequential condition and to the simultaneous condition. The brain kind of the brain's response in V1 is kind of the same for both of these. So there really is no attentional modulation of V1. In V4, on the other hand, which is a relatively later brain region, you find that V4 is where you get that attentional boost. In the complex situation, the simultaneous condition, you see that in V4, that's where the brain's response really gets improved in the simultaneous condition. Right here in V4, you're going to see an increased amount of brain response in V4 compared to over here. And the idea is that V4, one of that later visual regions, when you're really having to pay attention to something, because it's a task, you're paying attention to something and it's cluttered, it's complex, there's competition. V4 is the region. These later visual regions are the ones which appear to get the attentional boost. V1 doesn't seem to get much of an attentional boost. And that's kind of the general principle, or at least there's a theory, which basically says when you're paying attention to something, those regions of the brain which are most likely to be modulated are the later visual regions, or the later regions of the brain. The further you get from V1, the more likely you are to observe attentional enhancement, attentional modulation. V1 tends to not receive much attentional modulation. I do want to go over this finding a little bit. It's kind of a tough graph, and so I want to go over it twice. I do have some in-class discussion questions that I'm going to want to. There's some more stuff that I'll talk about next time regarding this chapter, but I think all the in-class discussion questions, I think I should be able to assign those today, and I want to get through this. Okay, so here is the graph, and these little traces right here, these represent signal change. You can think of them as activation. I think this is an fMRI, functional fMRI study, measuring blood flow, basically activation in two different brain regions, V1, primary visual cortex, and V4, which is part of the visual cortex, but it's relatively later, more in the top down, more in the perceptual, more in the interpretation side of things, more not very, this V1 is more sensory, V4 is slightly more in the perceptual side of things. And they're showing, I think the main one I want to focus in on is this one right here. This is the condition where people are asked to just pay attention. And that's what, in particular, that's what these blue lines are. So these are the trials. On some trials, people were not given a task. They were like, just look at the stuff. On some trials, they weren't told to pay attention. They're just like, look at the little square thing, colorful square things when they appear on the screen, but you don't have to respond at all. Just look at them and that's it. Passively view them. That's what the ones without the blue, that's what these are. Passively viewing things, and you're not having to attend to anything or respond to anything. That's what these are. The blue vertical lines, these are those trials in which the participant is asked to attend to a target. One of those blue color square thingies is a target, and you have to attend to it, or you have to make a response to it. You have to kind of you focus in on one of those one of those colorful square thingies. And these are the blue vertical lines represent those trials where you have to attend to a specific thing. And once again, these little traces, these represent the amount of activation in each brain region, V1 or V4. So a key comparison is the difference between like the simultaneous condition when you don't have to pay attention to something compared to when you do have to pay attention to something. And in V1, you can see that these traces right here, they're about the same height. So in the simultaneous condition in V1, you're in here, in the blue trace, you're asked to pay attention to something. And in V1, you don't really get much of an attentional enhancement. So these are basically the same height. Simultaneous, there's a lot of clutter, but you're just asked to passively view. You don't have to pay attention to anything. In the simultaneous condition, where there's a lot of clutter, but you are asked to find a target, you're asked to pay attention to a specific target. You don't really get that much of an enhancement in V1. On V4, on the other hand, this is that relatively later visual region. V4, you do see an enhancement. Once again, so for the simultaneous condition, right here, this is when you're just passively viewing the complex environment. You're not asked to focus in on anything. You're just looking at that and you're not focusing in on anything at all. That's the brain response in V4 when you're not focusing in on anything, but it's a complex, simultaneous, all four color squares are appearing at the same time, but you're not asked to focus in on any one of them. In the blue vertical line condition right here, you are asked to focus in on one of them, which is the target. And you can see that there's a difference in activation between these two right here. In V4, you see that attention causes your response in V4 to increase, whereas attention in V1 does not cause an increase in the response of the brain. So there's attentional modulation in V4, as illustrated by this increase right here, but there's not attentional modulation in V1, as shown by the fact that these two traces are basically the same height right there. So that's a lot of stuff related to this bias competition model. We're definitely going to review some of that next time, but I think I have these questions. Make sure that we can all do them all. We'll be covering a lot of this stuff next time, but I want to, yeah, but we can't answer these. So these, I'm going to have these questions and I'm going to have these due Friday at 11:59 p.m. So that should be plenty of time to answer these three questions. And you'll turn these in the same place we always do. And so those three questions is, what are the difference between frequency analysis and event-related potentials? We've covered this a lot now, but this is an important distinction. I've covered this in chapter 3. I cover it again in this chapter, and I just want to make sure that you understand the difference between frequency analysis and ERPs. The differences between endogenous or exogenous. Endogenous is voluntary, exogenous is involuntary types of attention. And then what I was just talking about now, I want you to see kind of the similarities between extinction and this idea of biased competition. Both are talked about in your textbook, so you can use your textbook to kind of help you answer this last question. Are there any questions or comments before we cut out here regarding this assignment? Okay, so this will be due once again. I'll post it. I'll post the due right now. I will post the place where you can turn it on. It will be due once again Friday, 11:59 p.m. So have a good weekend. I will talk to you later.
Thank you.
You're welcome. Talk to you later. See you later.